Hi, welcome back. This is clip 1A, and I hope to give you a practical demonstration of how electricity is generated. The electricity you receive from a battery is it is stored energy, and it probably took a lot more energy to produce the battery than you will ever get out of it. If you want to produce electrical energy in any quantities, you must generate it in a device for the purpose. So, in doing that, there's a very important concept that needs to be understood, and that's the process of induction. And about early 1800s, around that, a connection was made between magnetism and electricity. I have here two magnets, and they play up a little bit. They have a mind of their own. I've marked each one, wrapped white paper around them. They're neodymium magnets. They're very strong. Red on one end indicating the North Pole, and blue for the South Pole. So each magnet has a north and south pole, just like an electrical current has a plus and a minus, or negative and positive orientation. So here we are now. If I put two likes, the blue and the red, they stick together, no problem. Opposites attract, and like repels. If I put the two reds together, try to put them together, no matter how hard I push, they'll resist. I cannot possibly get them to go together, no matter how I try. If I tried the two blues, I'll try and let you see there against the white background, they won't go together. Here is a plastic, like a little tube with it stopped on one end. I just drop one magnet down into it there, and the blue end is to the bottom. So if I put a red up against it, it will stick to it. You see it there. If on the other hand I try to push the two blues together, the one in the tube will rise. It repels. Now if I drop the red of this down into the tube, hopefully you can see it there, it won't. It will not go down. The two will not go together. It's levitating there, because likes repel. Now another form of a permanent magnet is a ring magnet, such as this. It's just a ferrite magnet, not as powerful as the earlier one, but it still attracts. You see it there. So it's still a magnet. Now, the other way of making a magnet is to take a coil, and this is a simple coil here. All it is a piece of mild steel, about the length of a fountain pen, and around it is wrapped 250 turns of insulated copper wire. You can see it there. There's a piece of insulating tape just to keep it in place there. So it's just wrapped around, and importantly here, if you look at it, there's two little conductors, two wires coming out. So each one of those, one of them just wraps right around and it comes out in the other one. So they're the connectors. So if I take this battery here, put on my glasses, and here is a lid of a box, just a lid of a box. That's all it is, tin box. And if I try to get it to stick, it won't stick. If on the other hand I attach the battery to the electromagnet, it sticks. Now, just to show you that again, because it may not have been in the right place, here's the lid of the box. It sticks. Now, what's happening is that the current in the battery, the direct current in the battery, is going around the coil, and that's creating a magnetic field. And the direction of that magnetic field, whether the north is here or the north is up here, depends on how the wires are connected to the battery, negative and positive. By reversing the direction of the wires, you change the polarity of the magnetic field. What I'm going to do now is I'm going to try and disconnect the wires, and I expect the lid of a box to fall away because the magnetic field will be gone, right? And so far, so good. So we put away that battery, it's not needed anymore. And we're now going to show you another somewhat somewhat interesting contraption. But before I do, another interesting contraption. We're going to show you this diagram here. As I said, electromagnetism and electric current are connected, as I've shown there. Now, in order to create electricity, you first of all need a coil, and I've shown you this coil already. And then you need a load, and the load in this case is just a little battery. Yeah, and it's a bit tight to open. And I just want to show you that there are no batteries in there. No batteries. See that? There's just connected wires. That's all. No batteries whatsoever. Okay, so it's just a little torch, hot wired. That's all it is. So I connect both ends of the torch to the coil, and the idea is to induce a current in here. So it works like this. The bulb is here, the coil is here. So in order to induce a current in the coil, I need to bring it under the influence of a magnetic field. So I'm doing the reverse really. In the case of making the magnet, we put the battery here and we got a magnetic effect. This way we're putting the magnet here and we're getting current going the other way. But there's a very, very important principle involved in this magnetic field. You cannot generate electricity by just taking any stable electric field produced by a battery in a coil or with a permanent magnet and get the light to light. Do you see it there? I'm just trying to show it to you. The light will not light using a permanent magnet or a battery ordinary magnet. And if I show you the two very strong little magnets I had before, and they always have a mind of their own. In fact, they can be quite dangerous if they clip your fingers together. So I put the blue here, the red here. No light occurs. Sorry, that's the back of it. No light occurs. There's no light. So just to show you there again, take it away, put it to it. No light occurs. The light does not come on. And if you think about it, this is nature's way of ensuring that we cannot produce electrical energy out of nothing, because otherwise a city could come along and put up build a huge big permanent magnet, put a coil into it and drive all their street lighting without any energy going in. This magnetic field must change in intensity. It must change. So if the pull between, let's say, this little magnet here, placed, we'll say there, was 2 kilos on, let's say, the coil. So if it's 2 kilos of a pull, and that were to go up to 8 kilos, then that increase in intensity, even if it's in the same direction, would induce a current. So the difference there would be 6 kilos. So the current would be induced by the changing of the intensity from 2 to 8 kilos. So it doesn't have to be from north to south. But in practice, the really good way to produce your power in the coil is to alternate the magnets on a rotor from north to south. And each time you bring the north up, a current flows. And every time it passes by and it decreases, the current collapses and it flows the other way. And when you bring in the south one, the same happens. So you're reversing the process all the time. That's really how it's done. And that way you have to input energy. Now I'm going to show you a little device here. It's a fairly crude little thing. It's basically a motor, an electric motor, which it has nothing to do with this except it's designed just to drive the experiment. It could be an engine, it could be a little steam engine, or it could be a bicycle with a chain on it. It could be any motive force. But the most important part of it is that here is a disc, and I'll show you this disc again. Now please ignore the whole lot here and in these little devices here. On the disc you have 4 magnets, and they're marked red and blue very faintly. The two red ones are two North Pole facing magnets, and the two blue ones here are two South Pole. So four little holes, 20mm in diameter, have been drilled part ways into the piece of aluminium, and these magnets have been glued in place so that they can't come out, and they can revolve. You see them there going around like that. They can revolve, and the idea is that as these revolve, any coil in their vicinity will experience a magnetic field which will vary from north to south and back to north to south again. So, in order to try the experiment, I'm going to bring the camera up a little closer here where you can see it. And I've discovered recently that most camcorders cannot be paused when in record mode, and it's a nuisance because I could switch it off there and save some time, but you can't do it, and it's something to look for if you're buying a camcorder. Can it be paused in record mode, whatever reason you might have for it. So now what I'm going to try to do here now, and hopefully it will work, is I'm going to bring this coil here up to the magnets as they go spinning round, and hold it by hand. And the reason I'm holding it by hand is that I want to just show you in the crudest possible form the process of induction taking place, so that there's as little mechanical elements to it as possible, and I have the little human element. So now I'm going to switch it on, and as I do, I'll bring the magnets up. And as I do, you see the bulb lighting. Okay, so now I'm going to turn off some lighting here, make it a bit duller. Do it again. See the bulb, it's out now. The bulb is not, now the bulb lights. And the intensity of the bulb, the light, depends on how close I can get it to it. And also, if I move it out slightly, out towards the edge of the disc, it brightens a bit as well, because it's the speed is greater there. So each magnet is causing a current to rise in the coil and collapse again, and that is creating, inducing a current in this coil here, which in a motor would be known as the starter. Now I'm going to just be a bit more adventurous, and be nice to see this in almost total darkness. Alright, just get the switch there. Now, and again, it's hard to see it, but we'll try it. And there you can see it there in total darkness, lighting up my hand on the equipment. Now this is not the best practice at all. It's just to show the thing again. So that's it, just to show it to you again, working in light. Hopefully it'll work. You see it coming on. So right, we'll just put that down there for a moment. I'll disconnect this, and I want to show you just a little more about the device. I built this little thing myself just for you, especially to see, I'll take out this, and you can see there that it's just a disc machined, and the four magnets here, and these go round. But also to look at here is the actual little device itself. There are four corresponding iron cores here, which correspond with the magnets, and around them, then you can see it there, are wrapped coils of wire, coils of insulated copper wire, and they're all connected up in series. Each one connects to the rest, but because two of the magnets are opposite direction to the others, two of the wires coming from the windings have to be reversed. Now, it's a bit complicated, you won't see it there, and it's very rough and ready. But in any event, I'm going to install the disc back on, only this time I'm going to put these magnets facing inwards. The last time they were facing out so that I could put the coil up to it. So this time we'll put them facing in, so they'll be going against the little starters, which will be stationary, and they'll be more held in place by a machine as they would in reality. And the idea here now again is we're going to produce an alternating current as it would be in a single phase alternator, or indeed the dynamo of a push bike does the very same thing. So again, we get our little light here, and get out and connect it onto the terminals of the alternator. Switch on the alternator, and there the light comes on. So if I can just put the light off now for a second. And there you see quite a little bit of light, and if I shine it up here and I move the camera on the clipboard, you see the coil that I showed you earlier there. If I pull it back a bit, you might see it a bit more clear. See the coil that I showed you, and the magnet diagram, and then over here then is the bulb. So it's illuminating its own diagram, as it were. So it's a nice little thing, and it just shows the process. I'm going to turn on the light again. And that's the process of induction. One little feature of it is that if I turn off the motor, it takes a little moment for the bulb to go out, and that's because the weight of the motor and all of the things that go around, including the magnets, tends to go on a bit. It tends to run on, just like if you lift a bicycle up off the ground and spin the back wheel with the pedal. When you stop the pedal, the wheel will still keep going around. That's known as inertia, and it affects the phase, because as each one of these magnets pass the coil, the current reverses in direction, and that means it has a phase. The amount of times it does that per second is known as the hertz. It's called after a scientist who quantified it. But the thing is that if you have a lot of generators, as the Irish grid would have, or the Irish producers would have, and they're all burning coal and oil and all that sort of stuff, they all have to be brought into the same phase, and they have an inertia. So it'd be hard for any small device or any small generator to change that phase. And similarly, if you put in a few windmills into the system, the phase will stay with the mains. The frequency will be with the mains. However, if you increase the windmills to so much that there's nearly more of them than there is conventional power, you could have problems with this inertia, in that the inertia of the windmills would be greater than the conventional generating plant. So it can be a bit of a problem. So that's what inertia means. Simply means the length of time it takes for the device to come to a halt. So hopefully that was of some use, and we'll just rearrange the camera, disconnect and rearrange the camera, and just see if there are any other little pieces to explain about it, and I'll move it back here. Yeah, I think that's it. So basically, anyway, the purpose of this is to show you, and I'll put the light on as well, better. The purpose of this is to show you the process of induction, and how a magnetic field induces the current in the coil. That's the big thing, and that's the way all mechanical to electrical generators work. Of course, big thing that I must emphasize again is the field must be fluxed, and this is nature's way of ensuring that we can't produce energy out of nothing, because the fluxing process needs energy to drive around the rotor or whatever. The coil that stays static in a device like I've just shown you is called the starter, and the part that goes around is called the rotor. In a direct current dynamo, the starter is called the field, and the part that goes around is called the armature. Now, just to explain, an alternator creates alternating current, and a generator creates generating current. We might look at that in another clip. Now, they all produce alternating current, because you cannot produce direct current simply in any device. You have to produce it as alternating current, and you switch it back using a rotary commutator to direct current. So years ago, cars all had generators for charging the battery. Now it's alternators, just 30-40 years. And generators in vehicles they're obsolete. And the result is that we often call generators and alternators in between. It's debated. This is the purest term, is that an alternator produces alternator current, but in reality we sometimes call them generators, because they do generate current. So it's just I'm only letting you know that, so that you know if you hear it mentioned. It doesn't really make much difference at all, but just to note that it's just a term. Now, another little thing is that any generator or alternator, it will also run as a motor. So what I mean by that is, if you put power into this motor, it will spin, as we've just seen. But if you spun this with an engine real fast, you'd get a power out here. The only difference, in theory, in a generator and a motor is the speed. So if you have, let's say, a simple wind turbine, and the wind is very high, it will feed power into a battery. If the wind dies down, the power from the battery will run back into the generator and will drive around the turbine itself. But of course, there are devices to stop it doing that. Cutouts were the old ways, and there are other solid state devices to make sure that it doesn't work the other way. But in principle, a generator or an alternator will work either way. They'll work as a generator, or they'll work as a motor, depending on the speed. Now, our domestic supply in our homes is usually single phase. That means there's just one winding. That's all we have, just one winding like that. And it's alternating current, and it alternates at about 50 times per second. It has to be actually quite close to 50 times per second. My little device is alternating at about 45 hertz, which means that as there are 4 magnets for each turn is 4. So you divide the number of turns. You divide the hertz by 4, and you'll get the speed of the motor. So a quarter of 45 is 11 and 11.25 roughly. So that means that this motor is revolving at 11.25 times per second, and multiply that by 60 and you get its speed per minute. Okay, so some of that may be a wee bit difficult to understand, but I hope not. Oh yeah, that's the end of it. So the main thing we've learned about here is the process of induction, which is central to all generators and alternators, and I'd say that it's probably not fully understood by scientists. One thing that fascinates scientists is that a magnet actually always has 2 poles, north and south. They've never managed, as far as I know, to make one that has only one pole. So thank you very much. That's the end of that, and we'll see you then for part 1A. We'll have a look at 2 interesting characters and the result of their efforts, and hope you'll find it interesting. Thank you.